Hi, this is Madan. I'm currently pursuing my undergraduate degree in biomedical engineering from SRM University. The purpose of this video is to make a demonstration of our project work. Seen on the screen are the members of the group: Soundarya Rangarajan, Aditya Kashyap, Manoj Kiran, and myself. We carried out our work under the guidance of Mrs. Jayanti, Assistant Professor, Department of Biomedical Engineering, SRM University, Chennai. The topic of our work is simulation of lung representing the diseases bronchial emphysema and COPD using NI multisim and LabVIEW. Having done with the introduction, let's move on to the aim of the project. So the aim of the project is to develop a virtual simulation unit of the lung representing the diseases mentioned in the introduction. Moving to the objectives of the project. We start off by studying the anatomy and physiology of the human respiratory system. Then we consider specific diseases affecting the lung tissue at a superficial level. We then manipulate the components of the electrical analog to represent the pathophysiology of the lung. Since the model is an electrical circuit, the input to the system is also an electrical component. Then we check the response of the lung to varying ventilator input analogs, through which we arrive at an interpretation of the lung's response to the current ventilation parameters. Since the electrical model is analogous with the physiological lung, we extrapolate the response of the lungs to the same ventilation parameters. Finally, we develop a LabVIEW based system that can be subjected to real-time simulation, which can be used to analyze the patient's lung conditions before the patient is actually hooked up to a ventilator. Moving on to the pathology, we have considered two diseases at a superficial level: COPD and bronchial emphysema. COPD is a broad classification for the subclinical conditions emphysema, chronic bronchitis, and asthma. It manifests with a cluster of symptoms ranging from shortness of breath, coughing, to severe congestion in the lungs due to collapse of the alveoli. It is a type of obstructive lung disease characterized by long-term poor airflow. Bronchial emphysema is not a major disease by itself, but a hyponym of the major condition COPD. As you can see from the figure, bronchial emphysema involves excess secretion and accumulation of mucus in the bronchus and bronchioles and collapse of the alveoli. This leads to an increased airway resistance and inflammation of the bronchus and alveoli. Next comes the issue we would like to address. We all know that the ventilator is a life supporting device for patients whose respiratory system is compromised. Mechanical ventilation can be defined as the use of mechanical means to assist or replace spontaneous breathing. There are two major modes of ventilation: positive pressure and negative pressure ventilation, usually delivered to the patient as volume cycle, pressure cycle, or spontaneous cycle. Although a ventilator keeps the patient alive, it usually aggravates the pre-existing anomalies and suffocates the patient. Mentioned on the screen are some of the problems associated with mechanical ventilation. Barotrauma is a condition wherein the air reaches the interstitial spaces of alveoli instead of into the alveoli and causes the alveoli and the lung to collapse from pneumothorax. Volutrauma is a condition wherein the oxygen delivered to the lung is at excessively high tidal volumes, leading to damage of the lungs. Oxygen toxicity occurs due to excess oxygen delivered at high partial pressures. VALI, a lung injury caused by excess ventilation and causing a cluster of conditions called as ventilator associated lung injury when the cause of injury is unknown but has aggravated due to mechanical ventilation. VILI, a lung injury is called a ventilator induced lung injury when the cause of injury is only because of mechanical ventilation. Although lung protective ventilation strategies have been used to curtail the negative effects of ventilation, the number of cases succumbing to some form of ventilator induced injury is still significantly high. Moving on to the circuit analogy, we have used conventional analogies to represent and remodel the electrical equivalent circuit of bronchial emphysema, wherein a resistor is used to represent the airway resistance, inductor to represent airway inertance, capacitor to represent compliance of the lung. Seen on the screen is a remodeled circuit of bronchial emphysema. The circuit has three parts: the upper airways, the right and the left bronchus, the bronchioles, and the alveoli. The parameters altered are R4, R5, R6, C1, C2, C3 to represent the clinical condition. We remodel the circuit using NI multisim. NI multisim is a powerful circuit design software which gives us a platform to perform advanced analysis. For COPD, the parameters altered are R2, R3, L2, L3, R4, R5, R6, C1, C2, C3 to represent the clinical condition. The input to the circuit is a voltage controlled power supply producing square pulses with an effective on time of 1 millisecond to maintain the inspiration expiration ratio as 1:2. The connections on the left and the right ends are the hierarchical port connectors that can be used to control the input to the circuit once the circuit has been imported into LabVIEW. The proof for system stability has been performed using Methods MATLAB software. The stability analysis has been carried out by computing the step and ramp response decay times for a set of values of RLC. The step response decay times have given us an approximation of the stability of the system. If the step and ramp responses have the same decay times, it means that the system is unaffected by the type of input it receives. Shown on the screen is an example for simulation of step and ramp response of a system's transfer function for two severity cases. As seen from the table, the step and ramp response decay times increase for an increased value of R and a decreased value of C, as seen in a clinical setting wherein a severe pathology is earmarked by an increased airway resistance and decreased lung compliance. This proves the analogy between physiological lung and the virtual lung. Let us see how it works in MATLAB. Here, a step response simulation has been shown. A similar approach is needed for ramp response. As seen from the screen, this is the step response for the chosen transfer function. Moving on to the real-time simulation. Shown on the screen is NI multisim and LabVIEW co-simulation. After the construction of the circuit in NI multisim, the circuit has been compressed to make it accessible to the user in the LabVIEW screen. Once the ports are connected, the LabVIEW co-simulation terminals can be renamed for the type of input component they represent and the direction of usage, whether as input or output. When these steps have been completed, a multisim design VI preview is made available to the user. Once the construction of the circuit has been completed, it is imported into LabVIEW. The multisim LabVIEW co-simulation is carried out by using the co-simulation module. The co-simulation module is an add-on feature of LabVIEW that can be downloaded from NI website. The user can select the source of the file. As you can see, the circuit created in NI multisim is now compressed and only two ports are available, one for the input and one for the output. Shown on the screen is a proposed model of the ventilation assessment system's front panel that is controllable by the user. The enum operator has been used to allow the user to choose the disease he wants to simulate. A boolean switch to choose between volume and pressure cycle ventilation. The user can select the tidal volume or pressure by controlling the knob. The outputs for each of the system, that is pressure and volume cycles, is a waveform chart as seen on the front panel. A combined waveform for pressure and volume will be shown on the simulated circuit screen that would represent a volume versus pressure analogous curve. The block diagram shows a while loop, a control and simulation loop, a multisim module, an electrical input and a waveform chart output. The shown model is not completely ready for simulation purposes and is still under research to make it completely efficient. Besides being a real-time virtual simulation unit, this system acts as a ventilation assessment system for clinicians and professionals to learn and visualize the behavior of a physiological system to a crude input before dealing with the reality, which we believe would help them to take appropriate decisions not only to support the life of the patient using the machine, but also minimize the negative effects the procedure can itself have on the patient. thereby decreasing the post-operative care required and speed up recovery. And that concludes the purpose of this video. Thank you.